Hello, today I will be talking about the Archimedean property. So the Archimedean property states that the natural numbers in R are not bounded above. And this is the fundamental building block of any kind of analysis. And just for this video, we're going to assume that R is not bounded. There's a formal proof of, the real numbers being unbounded, but we're just going to assume that to be true for this video. And if we want to visualize this over here on a number line, we can see that n starts at 1 and then goes to 2, 3, 4, and continues all the way to infinity. Pretty simple, right? N is not bounded above. But from here we can deduce a couple other conclusions. So we'll say that n is not bounded above if and only if for all positive A and B, where B is greater than A and B are real numbers, there exists some n in the natural numbers such that B is less than n times A. And so we can visualize this with the number line as well. And we only care about B. This statement is true when B is not greater than A, but we only care about it when B is greater than A. Because like if B is negative, obviously there's going to be some n, right? So who cares? But this statement is basically saying that even if B is some crazy big number, and A is some crazy small number, because n is unbounded, you will always be able to find some crazy big natural number which will satisfy the inequality of B being less than n times A. So yeah, this conclusion isn't quite as useful as the next one that we're going to prove, but it's still good to think about, and you can see it here on the number line that I've drawn for you. So now the second conclusion is that n is not bounded above if and only if for every positive A in the real numbers, there exists some natural number n such that its reciprocal 1 over n is less than A. And this is very cool. I find this very cool, and I'll show you why here in a second. So we can visualize this again on a number line. We'll only be looking at positive numbers because we know that, 1 over n, the natural numbers are positive. So we can let A be some epsilon greater than 0, where epsilon is just some arbitrarily tiny number, 0.000001. And even if A is equal to 0.001, which can be written as a fraction, which is, I think that's, 1 over 10,000. But you can even go smaller than that. You can go 1 over, 1 bajillion trillion million. There will always be an n, a natural number n, which in this case we'll just take it to be 10,001. And its reciprocal will always be less than whatever we chose as our arbitrarily small a. And we can do this because of the Archimedean property, which states that n is not bounded above. And now just to go a little bit more in depth, let's look at the sequence 1 over n as n goes to infinity. And I'll just draw it out here for you. Or let me do a bit better of a job there. So if we go back to, calculus 1, we know that the limit as n approaches infinity of 1 over n is equal to 0. And this is, your basic asymptotic, function, right? You can see as, x is increasing, the function gets closer and closer and closer to 0, but it doesn't ever quite reach 0. And all of this is saying that, for all real numbers, with infinitely many decimals, you can always find something either slightly smaller than it or slightly bigger than it. And this leads to another, important concept in real analysis that says that the rational numbers are dense in the real numbers, which just means that if you take any two real numbers, there exists some rational number in between those real numbers. And now let's observe the domain and range of our function 1 over n. We know that the domain is the natural numbers n, right? And its range is going to be the set 0 to 1 where it's open at 0 and closed at 1. And what I love about this is it shows you the relation between a open set and a limit. And because we can see here that 0 is not contained in the range of that function, but literally everything else is. And this will be important, in any kind of analysis, topology, measure theory, because we don't care about the interior of these type of sets, really. We care about, the edge cases. And Archimedean property is us analyzing these open and closed, edge cases of subsets. And with that, I will end off the video. Thank you for watching, and stay tuned for more. And go check out my TikTok as well, Long Math.